PDF.
There's a PDF. It's easier in case any crash happens with the PDF. Download it.
Can I get that? Can I get this one?
Yeah,
Thanks.
should work. That will come. That will come in for a few more minutes.
Okay, can I get your attention, please? Shh. Thank you. Okay, so we are the BA Econ student representative coordinators.
Excuse me, everyone. Can you please give your fellow students some respect and listen? Everyone, can you please quieten down? Thank you.
Thank you. As I said, we are the BA Econ student representative coordinators, and we give you the chance to become a student representative.
Why don't you? I'll take a break after 5 minutes and you
Okay.
do it then.
You're during the break.
No, yeah, and I'll take a very early break. I anyway want them
you start
to.
and-
Yeah, I'll
Okay.
start and then
Okay.
I'll let you after 5 minutes or so.
Okay, thanks.
I'll
So
let you
we'll
go.
just wait
Okay,
here.
yeah. So it's difficult. It's difficult because they come in and. Guys, like every time, can you please make sure you squish together? Don't leave seats in the middle. Guys, no spare seats in the middle. Move together, please. Don't leave spare seats, please. Can you move to the sides, please? Okay, every time the same. Okay, no surprises here. Guys, can you just move up and free up some seats? There's still empty seats here, guys. Here, empty seats. Can you squish together, please? Okay. Empty seats, please move over. Okay. There's an empty seat here. Your backpack doesn't need a seat. Excuse me. Excuse me, your backpack doesn't need a seat, please. Here as well, can you please squish together? There as well, can you please move in? Can you please move in? Can you please move in? Thank you very much. Okay. I can see empty seats there, please, guys. Okay, so we can have an overflow room. Stop for Theatre 1 if you don't want to be so cramped, or a live YouTube stream of this lecture if you feel too cramped in here. Okay, that's your. Okay, so can I please? There are more seats down here. There are 2 seats down here. Okay. There's 1 more seat here in the front. I can see empty seats back there. Okay, let me get started, please. So, hello everyone. Okay, I leave it just up for those. So we have an overflow room. Again, it's Stopford Theatre 1, or for those who want to just sit outside in peace and quiet and listen to this. This is the live YouTube stream. Okay, if you want to use that, if that's too crowded for you. So, what are we going to do today? We're going to talk about continuity. Oh, sorry, you can't see that. Okay. Continuity and limits and differentiation. Continuity and limits of functions, especially continuity, is an extremely important feature or property of a function that will make life much easier. And we need to understand what it means. And then, of course, at the core of this entire unit is we need to be able to differentiate function. There's a spare seat here in the front row, if you want one. Okay. And so we talk about this. The reason why we need to think about these are as follows. Most, as you know, and we've explained that in a last week, that we use functions to quantify some economic variable, profits, utility, and we usually want to, at some point, we want to optimize these. And we usually do think about economic actors making marginal decisions. So decisions of, shall I do one more thing? Okay, shall I produce one additional item? Shall I consume one additional item? And that's how we think about decisions, so incrementally. And that means we're then thinking about how our functions, say profits or utilities, how these change as we move a little bit onwards. So we're making marginal considerations. This way of thinking in economics is actually a very old way of thinking, but it hasn't always been there. And just a little tidbit of economic history, one of the main early protagonists who introduced this marginal thinking is a guy called Stanley Jevons. And he lived, I need to look the exact dates up, from 1835 to 1882, and he worked here in Manchester. Had Nobel Prizes existed, he surely would have been one of the early Nobel Prizes in economics at that stage, because he introduced marginal thinking. Not the only one, there were others at the same time. Okay? So, as we are making marginal decisions, that's when this concept of continuity of functions will come in extremely handy. Because what we are looking at is marginal rates of changes of functions, but it turns out we can only really calculate these if our function is continuous. I'll explain that in a moment, what that means. Okay, and towards the end of this lecture, or in the middle, we'll think very formally about how we determine what the rate of change of a function is. Okay, we call it the gradient. Graphically, it will be the slope to a function. Actually, that is a leftover that we're not going to talk about. So, before we start with this, I will soon do one little example. Berlin, where's Berlin? Some of you. Here. He was there in my office hour earlier, and he asked a question which I think will possibly benefit if I just go over that question. I think many of you will have that sort of issue. But before we do that, I'll ask our friends from the BA Econ Society, and please listen to them carefully. Oh, yes.
I'm glad to get your attention this time. So as I said, I give you this opportunity to become a student representative for the BA Econ program. What this means, a student representative is basically the voice for all the students, and they raise issues, and then they contact appropriate members of staff if they want to change anything. So this is the basic role of a student representative. They gather feedback from the lectures, they raise some issues, they work with staff to find a solution, and they let the students know the result.
But why? What's the reason of being a student representative? Here are several benefits. First of all, you have the chance to communicate with the academic staff, and you will be the link between students and the professors. And the most important thing is that you can have the opportunity to change some things. And also you can, at the same time, to improve your skills, such as communication and interpersonal skills, and to boost your employability. Also, it's a very good thing to write on your CV. And as you all know, there's a Stellify Award, which needs you to have the leadership role, and the student representative is one of them, which would go on your transcript and to boost your employability. And if you want to join us, there's an email, we sent it yesterday. You need to submit an application form. And if you have any questions, you can email at this. This is our email, and any questions, any problems, you can send it to us. Thank you.
You're fine? Okay, thank you very much. I can only... Do you want to? I'll just close it. You're locked out. Okay. I can only reinforce this. It's super important that every program has student reps, and they're super important. And it's great for those like you that you volunteer your time to help your cohort of students to be represented. So thanks to you, and I hope many of you will consider becoming a rep. So, with that, back to the topic. So, so Berlin came and asked a question from the textbook, because in the textbook there are lots of questions at the end of chapters. Turns out, first thing Berlin learned, that there was a little sign or indicator SM next to the question. And that means that whenever you have a question in a textbook with SM stands for student manual, then the solution to this question is in the student manual. And if you go to Blackboard, to the course information, at the end of the reading list is a link to the student manual. Okay, so I think many of you will find that useful. But here is the question. Here's a function, and the question was find the domain for that function. Okay, and it was very clear that there are several ways how the domain for this function can be restricted. Okay, so firstly, there are two mathematical operations here which don't work on every real number. Firstly, a division, and therefore we can't divide by 0. So this term here, the denominator, couldn't be 0, and that would immediately rule out x equals 2 and x is equal to -3, because either of these two values would make one of these two terms 0. Okay, so these two values we can't have in our domain. That was the first thing, and fairly straightforward. Then it was very obvious that we have the square root, and that means the argument to this. Perhaps it doesn't like the shiny pen. And so the argument to the square root had to be non-negative. So how do we go about thinking like this? There are several ways how you can think about this, but I wanted to show you one which I find the easiest way to think about this. So we are concerned about these three terms, and we know that if either all three of them or one of these three terms is negative, then the whole thing will become negative, right? Okay. So this is the way how I think about it. I draw a number line, and I realize that there are three important values here. Important values in the sense that at these values, one of these three terms will change its sign. We have two of them already here. -3 is one such value, because this term will change sign. 2 is another value where this term will change sign. Okay, smaller than 2, and this will be negative. Larger than 2, this will be positive. And the other value is 1. Okay, so that means we really, if we want to consider whether this term is positive or negative, there are 1, 2, 3, 4 regions we need to consider. Okay, so let's write these three terms down here, x minus 1, x minus 2, and x plus 3. So now we can think about what happens to these three terms in these four regions. -3, let's look at the first one. If we have values for x smaller than -3, this will be negative. If they are between -3 and 1, that term will also be negative. But as soon as x becomes larger than 1, we will have positive. This term will be positive, right? So let's look at this term, x minus 2. Well, it's this value that's important. If x is larger than 2, this will be positive. But if x is smaller than 2, in all these four, the remaining three regions, we will have negative values for this term. And then the same with this one. Basically, that will be negative here, but positive in all these three regions. Okay? So, now we have basically the product of these three. It's the division, but it's in terms of the sign, it's as if it was a product, okay? All three are negative. That means the entire term, let me call that A, just for short, A. So the entire term A is going to be negative. Here, negative times negative is plus, plus. This will be plus. This will be negative. And this will be plus, right? So we already know this region here and this region here is out of bounds. Because in these regions, this entire term A would be negative, and hence we couldn't calculate the square root. Okay, so we're left with these two regions. Now also note that we have these two special values here. X equals 2, we can't have that one, and x equals -3, we can't have that one. So now we can see what the domain for this function is. So in here, but x needs to be larger than -3. It can't be equal to -3. But it can be equal to 1. Okay, so this one. And x has to be larger than 2, but it could go anywhere up to infinity. Okay, so in some sense you have two sets here, and the domain is the union of these two sets. Okay, but you could also say it in words. You could say x needs to be either in this interval or in this interval. Okay, if you wanted to do it so you could also say that x has to be element of this interval or element of this interval. Okay? Either of this works. Okay, so when you have complicated functions and you need to evaluate, perhaps you need to sketch the function. That was one of the online clips on polynomials, ask you to do that. Or you need to determine the domain. Try and make your problem as small as possible. Try to only think about where does something change. Okay, and you get a limited number of sets, and then you think about those. Okay, so thanks for asking earlier, Berlin. That was super useful. Put that aside, and let's continue. So, limits of a function. Most of you would have heard about this, so there's possibly just going to be a revision. So let's say we have a function here. F of x is 1 over x plus 1 for all values of x larger than 0. Okay? We set that as a domain. So we say the limit, I'll give you the result first, and then we see how we get there. The limit of this function, as x goes to infinity, so as we go as far as we can to the right-hand side, is 1. That's not to say that the function will ever take the value 1. Will the function ever take the value 1? No. Okay, because however large x becomes, we have 1 plus something, even if it's very, very small, but we have 1 plus something. Okay, it's just the limit of the function that is 1. We sometimes also write it like this, but it's the same thing. Okay, the limit as x goes to infinity of function f of x is equal to 1. Okay, these two things say exactly the same thing. What about as x goes to 0? So what if we say what happens as x becomes smaller and smaller to 0? Okay. Now we can't go to 0 because 0 isn't defined. Okay. So what we say is that as we go towards 0, the function will increase, will become larger and larger. So the function will go to infinity, but the limit is not defined. We can't go to 0. Yeah?
Can we define x go to 0 plus? 0 plus.
To 0 plus, we could. Okay, we could say that. Okay, and now I would need, so are you asking, could we say the limit of x going to 0 plus is equal to infinity? Okay, let me think. So this is quite possible that you can write that. I'll need to check whether that is okay to write it like this. Okay, let me put a little proviso there, but I'll let you know. So we already said we are never reaching 1, we are just getting closer and closer. So you know we are mainly interested later in finding optima. This is the type of function where we immediately realize there is actually no optimum, right? There's neither a minimum for this function, nor is there a maximum. Because we could always go to larger values of x, and the function would always go smaller, would always become smaller. And we could always go even closer to 0, and the function would still become larger. Okay? So we will not have a maximum nor a minimum here. So the limit, so in other words, you can say the limit of the function doesn't actually evaluate f at infinity, because there isn't just one value at infinity. We can't evaluate the function. We can't plug in infinity and say that's what we get out. It's merely a description of how f behaves. We could think of investigating the limit of a function, or the limiting behavior of a function, actually near any value of x. But there we need to be quite careful, and that's where the concept of continuity comes in. We will come back to this slide. Okay, let's go to the next slide. I'll refer back to this. Both these functions here are what we describe discontinuous functions. Okay. And there's a definition, very useful definition for this, or how you can think about this. Okay? You can think about this, a function is discontinuous if you cannot draw the function over its entire domain without, and this is where the very technical term comes in, without lifting your pen. Okay, so a super technical term. So when you think about it, if you think about it, that's super obvious. This function here, 1 over x, now defined over all real values unequal to 0. You can't possibly draw this in one stroke. And the same with this function here. You can't possibly draw this with one stroke. I would have to lift the pen to jump up here. Okay? So if you want to, for yourself, be able to understand what a discontinuous function is, it's one which you can't draw without lifting your pen, or vice versa, a continuous function you could draw in one stroke. Okay. So, here's a more formal definition of what a continuous function is, if that isn't technical enough for you. So function f is continuous at point x if the limit of that function as we go towards a, so the limit of that function fx as we go to a is equal to f of a, and that implies a number of things. Firstly, f must be defined at a. Okay? And that's why this one doesn't work. Okay? That leaves still open being able to write this, because f would be defined at 0 plus. Okay? The limit of f as x goes to a from whichever side of a must exist. And this unique limit must be exactly equal to f of a from whatever side we come. So continuity at a requires agreement of limiting behavior from whichever side we approach. So let us go back here. Let me just pick any point here. Okay? And we can think of, so here's x, this is the x-axis. We can think of approaching this function from the right, and as we get closer and closer to that point, at let's say that's x equals 2, as we get closer and closer, that function will get closer and closer to this value, okay? F of 2. If we approach from this side. What happens if we approach from this side? The function value will come down, and the closer we get, it will approach f2. And at f2, the function is defined, and the limits from both sides agree with each other. So that's a continuous function. So, we could think of the value 0 here, which is the point of discontinuity for this function, but let me look at this other function. This is a stepwise function, or stepwise linear function, we sometimes call this. So it's defined with different equations for different segments in the domain, but it's still a function, because for any value of x in the domain, it uniquely defines one value of x. Okay, so it's still a function. But that's why if we also had an equal here, it wouldn't be a function anymore, because then it would define or give us two values at the value of x equals 2. Okay, and now we can't have that. That would be a naughty function. That's also not a technical term. So let's think about the discontinuity here. As we go, so the function is defined at x. That's a tick. So think about these 3 points. It must be defined at x. Okay. We have a limit from here and a limit from here. The limit if we come from x larger than 2, so as we come from here, this is the limit. As we come from x smaller than 2, as we approach from this side, this value here is the limit. But the two limits do not agree. Okay, because if we come from here, the limit is 6. If we come from here, the limit is 4. So this step means, as we come from both sides, the limit doesn't agree. Okay, so it's discontinuous. This function is also discontinuous at that point. Discontinuous functions are really difficult to handle. And let me just briefly show you why. Especially for the purpose of making these marginal considerations. If you make marginal considerations, we are thinking about slopes. All of you will already know what the slope of a function is, even though I will formally define it in the next few minutes. You know, it's sort of, it's the slope of the tangent at a particular point. Right? That's the slope of a function. Think about the slope here. We have a tangent, this is a linear function, so the tangent is just the same as the function, and it has a slope. But what about at this point? At this point, you could think this could be the tangent, but it could also be this, right? All of these only touch the function, okay? So it's not really, it doesn't really make sense to think about the limiting behavior or the tangent of a function at such a point. That's why discontinuous functions are really difficult to deal with the tools which we will teach you. And therefore it's important to know whether a function which you want to optimize, whether that is continuous or not. Now, can you think of reasons why we could have in economics, why we could have discontinuous functions? Yeah? Okay, super. That's one reason. You could think of, if you, let's say, spaceships. Okay, there are some companies which produce spaceships, but they're in very small numbers. And you can really only think of a cost function if you produce 1, or perhaps 2 or 3, but not 2.5. And since you produce so few, it really matters. Whereas if you were to bake rolls, of course, you can't really bake half a roll. Well, you could, but let's imagine you could only bake entire rolls. But since you're producing millions, the fact that half a roll isn't really defined really doesn't matter. Okay? But there's another reason. Let's say you're a company, you have some sort of a big factory and you're producing, and there's some sort of range in which you can vary how much you produce. And the more you produce, it becomes more costly. But if you are reaching the limit to produce one good more, you would perhaps have to build an extra factory. And then immediately your cost function will immediately jump. Okay? So often when we are making these marginal judgments, we have to be careful actually to understand that we're really only making these considerations for being able to make small changes. And in certain circumstances that's not appropriate, but because perhaps we need to produce this extra factory. Okay? And in some sense you can think about everything. If you just think big enough, everything is discontinuous. Okay, but in the often there's a reasonable range of values over which we optimize where we can reasonably argue that the function is actually continuous. Okay, so okay. Some of this I think will be repetition for you, but there's absolutely no harm to repeat that. At the end of today, so what we're now going to go through is really, again, the nuts and bolts of what's the definition of a tangent. For most of the course, what's important is that we can find slopes of a function, okay? And we fortunately have very useful rules to do that. And we will deploy them almost always. But let me briefly remind you how we define a slope. So here's a function, the red bit, that's this function here. Okay? So if you just take 2 points here, P and Q, and draw a line through these points, then the slope of this line, we know how to calculate this. We're taking this difference here, this difference in x, and we call it delta x, the change in x from this point to this point, so it's approximately 3 units here. And we calculate how much the value of the function changes over that interval. And the slope of this line is delta fx divided by delta x. Okay, and how we calculate that delta is we take the function value at x plus, so this value here is x, at x plus delta x, that's this one, x plus delta x. And we take the function value here, and we subtract the function value at the value x, at this one. Okay, so this is all going to be very familiar to you. And if we are interested in the value of the tangent at this point, then what we do conceptually is we'll just move this chord until it only touches the function at that one point. Okay? And really what we've done then is we've made this delta x smaller and smaller. Okay? But the definition of the slope will still remain the same. Just that this delta x will become smaller and smaller. Now, as that goes smaller and smaller, we will change notation, and instead of delta x, we will write h. Okay? That h here is really used instead of delta x to denote a very small change. And what we want is, we want to understand how does this slope behave as this delta x becomes 0. Okay, so what you can see here, this formula is basically this formula where we replace the delta x, so it's this formula here, where we replace the delta x with h, because that x and x cancels out, and then we are asking what is the limit of that function, we just talked about limits, as h goes to 0. And that's what we call the slope. That's what we call the slope of this line. Okay? So the slope of this is f prime of x. So the slope of f at that point. So we call that f prime of x, but there are different ways of writing that, and you have to be familiar with all of them. D of f over d of x. Sometimes we call it d of f x over dx. Sometimes that's just written like this. It's of course exactly the same. Okay. Or that form d of f dx. So these are all the same things. Okay. So f prime of x1 gives the slope of the tangent to the curve y of fx at point x1. So if we label this x1, it would give us the slope at the function evaluated at x1. So it's important, the slope really changes, of course, for this type of function wherever we evaluate it. So this is now, there's an important subtle point here. We said f prime of x1 is the slope of the tangent to the function y equals f of x at the point x1, y1. Or y1 is exactly the same as f evaluated at x1. Whenever we have a subscript here, that means we are looking at a particular point, okay? Coordinates at a particular point. Whereas if we don't have these subscripts, these are really variables. Okay, so we say, okay, anywhere in the domain X or anywhere in the range Y, but if we put a subscript to it, then we are pinning it down to a particular point. That's important to internalize. Thank you. Won't be the last time that I forget about checking this. So, here we have the function. Here was our point P. Here is my slightly crooked interpretation of the tangent. So sometimes we will want to know, actually let me first label this again. So that is x1. This is f of x1. Sometimes we need to know what the equation for that tangent is. So the tangent is a function again, right? Okay, at different values of x, it has different values. And sometimes we want to know the function, okay? You know, of course, you know, this is a line. You know, lines usually are represented by something like this, right? A plus bx, where a is the intercept, so that would be here, and b would be the slope. Okay. Now I tell you that the equation for the tangent looks like this. Let me on the next slide show you what that means in terms of this representation. But importantly, before we do that, here we have a mixture of these x's with or without subscript. So some values here are variables and others are just particular values, particular points. And the variable is here and here. Everything else will just be a particular value. But that is a variable and that is a variable. So that is going to be that y and that x is going to be that x. And all the other terms will somehow combine to be the intercept and the slope. Okay? And that we're going to look at in the next slide. Okay? So, we'll go back to the definition. So, here's again what I've replicated for you. And let me convince you that this is right. Okay? All I'm going to do is a bit of algebra. I'll bring that fx over to the other side. So I have that here. Then, see where the variables are. Here we have a variable. Remember what we are aiming at. We are aiming at something that looks like this. Okay? So we have the y here, so that's pretty good. And we have an x here. So the right-hand side still looks a little bit messier. Okay? So what I'm now going to try and do is to isolate that x, because I want to have this equation in this form. Okay? So here we have f prime x1 times x, that is this guy here. But I also have f prime x1 times x1, and that has a minus. So I have here minus f prime x1, x1. So now you can see we have a value, a value, a value. This entire thing is just a constant. Here I have my variable, so I've isolated it, and the factor in front of it, that's the slope. And that's, of course, f prime x1, because that was sort of the definition, right? The slope of that line is the first derivative of that function. But what's the intercept? The intercept is f of x1 minus f prime x1, x1. This is this guy, the a. Okay, that is f of x1 minus f prime evaluated at x1 times x1. Okay, that's the a. Sorry, I ran out of space here. That's equal to the a, the intercept. Okay, so this is how we typically express the equation for the tangent, and I just did that to convince you that really this is nothing else than the definition of a line. Okay, so we also call that the linear approximation to f at x equals x1. So at this stage, we use this term f prime of x1, the slope at the function. I haven't talked to you yet about how we calculate it. Okay? Absolutely not. Now actually, before I go through this, let me just quickly jump a couple of slides. Okay? Because I'm going to derive the function or the slope of a function sort of from first principles, but fortunately, it turns out we don't usually have to do that. Okay? Because typically, when we calculate the slope of a function, we don't have to calculate this entire thing, or this thing on the right-hand side, because that looks slightly nasty, right? And we have to evaluate some limit. We don't really want to do that most of the time. So typically we will have some convenient rules to find f prime x directly from knowing what fx is. Okay? Without having to invoke some sort of limit and to calculate terms like x plus h, f of x plus h. That's really, h is very small, so we have to deal with very small numbers. That's usually quite nasty. And without having to calculate limits for h going to 0. Okay? But I do want you to understand that we could use this equation to calculate the limit of a function. So, I'm not going to rush through this. What I'm going to do is I'll record an online clip for these next 4 slides, okay? And I'll publish that hopefully tonight. Okay, so I have another important message. Okay, can you please? That's you. Everyone, can you please quiet down for a minute? Just a minute. Okay. I need to repeat one thing. Next week is tutorial, the first exercise class or tutorial. The tutorial sheet is available on Blackboard for the next week. On that tutorial sheet, it will say that I expect you to solve the first, I actually can't remember, 2 or 3 questions. It will say on top of the tutorial sheet. Do solve the first few questions, because we will not go through them in the tutorial. You will get time to discuss with your neighbors and compare answers, and we will tackle problems. Okay? Have a great weekend. What's your question? Yes. Okay. Why that?